Okay, let's get back to our root finding methods. So just a quick recap. When I'm saying I'm finding a root of a function, I'm looking for a value that will zero that function out. And so we're looking for, that's what we, whether we want to zero out the function or find some sort of, there the function is a constant value, doesn't really matter, we just agree on the zero. I can always recast the problem slightly differently. So a lot of different engineering problems can be basically converted into this. I'm looking for x such that f of x is equal to 0. And both for this lecture and for the knowledge base, you will need to know how to cast the problem as a root finding problem, as well as apply a method and program a method to actually do it. Okay? So there's two parts of it. One is basically formulating your problem correctly, and the other part is actually solving it. Okay? Excellent. So we have started the lecture with our first method, which is called Bisection Method, which basically says, all right, identify an interval where this zero of the function exists, and then essentially keep halving the interval and figuring out at every step which half to keep moving forward and which half to discard. And at some point just stop when your interval is small enough, because then you will be close enough to your value that you're looking for. Okay? Sounds like a sort of a reasonable thing to do. And in your exercise, so what I want you to kind of do on your own time, if you want to practice, we did this for this parachute problem. And there was a certain function f there that we were looking for. You can actually use an alternative function, f of x. And this is just like a different function to practice with. So part of it is a identifying interval. And not only that, this one is a little tricky. It's a polynomial. Polynomial can have up to 3 roots. Okay. So if you do this for an alternative function, question is, which root are you going to find out what it is? There might be multiple options. And something to think about or something to know about root finding is that you're going to, with the method as we did it last time, you're going to find one of them, if lucky. Okay. And it might be one out of many. So that's something to keep in mind. If you actually, let's say you have a bisection method and you identify an interval that has multiple roots inside, okay, very much possible to have a function like that, you're going to, again, find one of them. You're going to zero in on one of them. Okay? And which one kind of depends on the function itself, as you're going to which half you're going to keep. So that's something to bear in mind. The best is actually if you have, and some odd things can happen if you have multiple roots in that interval. Okay? So that's something to keep in mind. So give it a shot with this function. Again, there are 3 roots, so you're going to have to figure out which one you want to look for, and then look for that. Okay? Okay. Now, nothing about bisection method actually considers the function itself. Okay? I just halve the interval and keep halving the interval itself. So I'm never really considering the value or the size of my f other than looking at, oh, is it positive, is it negative? So technically, if I have these u upper and lower parts of the interval, I could say, okay, well here the absolute value of f is much smaller than on this side. So technically, my root should be closer to this side, right? And in bisection method, I don't do that. So bisection method is one of the slowest methods because of that. It kind of moves at a determined speed, okay, and no faster than that. So there is a number of methods that we're going to now consider. They're trying to speed that up. the simplest way to speed things up is to, okay, I don't know how function behaves. The quickest way to see how the function changes is considering its derivative, okay? And that derivative is approximated always by a slope of this value minus this value divided by the difference between them, okay? That's my cheapest way to figure out what derivative is on some interval. And the larger the interval, the larger the error I make in the process. But hopefully, if things work well, in this method, I say, this is my approximate method, approximated basically just by this linear version of this. Okay, so this is an approximation that I'm making. So I'm going to possibly get closer and faster to the root if I see where does this approximation intersect the 0, and set that as my next iterate in looking for the root. Okay. Do we see the logic? So momentarily, I'm going to evaluate f of xu and f of xl, so basically value of f at my endpoints of the interval. For the moment, I'm going to approximate my function, however non-linear it might be. I'm going to linearize it, okay? And the slope in between, here it is. Okay? This is my linear version. This black line is a linear version of my function, this one, okay? And its slope is f of xu minus f of xl divided by the difference between xu and xl. Okay? And I'm going to then say, well, 0 of that linear version is right here. And I can actually find what it is just by analyzing this problem geometrically. And I'm going to set that as my next iteration in root finding. And repeat. Yeah? Sounds also reasonable. But of course, it will also depend on the function itself and how far away it is from its linear version. My success will depend on how close my function is to that linear approximation of it. But this hopefully, so here on this particular interval, I would take this point, right? And this is a little closer to actual, this is my actual root I'm looking for. So sometimes it works well, sometimes it does not, but it's actually a value. So how do I actually evaluate this new, I'm going to call it XR still, okay? Well, from the geometry of this problem, value of f of xl, and this is actually negative here, divided by xr minus xl, so this divided by this has to be equal to this divided by this. Right? This is because these two triangles are similar. Okay? So they're proportional. And that's actually written here. And what we did take into account is who is negative, who is positive. So basically, it works out as this. And then from that, I can find what my XR is. So that's my next step. And then I'm going to still behave as in bisection method. I'm going to look between XR and XL and XR and XU. I'm going to take subinterval that has the same properties and in bisection method, the bracket properties, right? So I still have to have that my f evaluated f of xl times f of xr. In this case, it's positive. So I'm actually going to take this xr to xu as my next interval. So the code is actually pretty much the same as bisection method. I'm just going to change how I evaluate xr. Okay? And I'm going to find it from here. So essentially, you can, from your bisection method, really quickly change it to this false position method. And I'm going to do that right now by basically just changing how xr is computed. Instead of a midpoint, I actually have a formula, and I can obviously see that that formula takes also values of f into consideration, unlike that midpoint formula. So hopefully that works better. Let's see for this. There's never really a guarantee of how fast this works. It does depend on the function itself. I'm gonna navigate because I think I closed my... I'm gonna navigate to my teaching. Okay. Apparently I can't do anything. Box sync, teaching. Here, there. Grade 10. So this was basically my problem, my parachutist problem, using bisection method. Okay. So I'm gonna actually just copy it. And now I'm gonna change the code to false position. So false position is still a bracketing method. I do have to have this interval, and I already identified interval for parachutist problem. So I have it as 12 and 16. And here, instead of this midpoint, okay, I'm changing it to xr is equal to xu minus f of xu times slope inverse, essentially. Xu minus f of xu divided by f of xl minus f of xu. Okay. And that's really the only change. So this is what's called reusing the code. Always a good idea, because all of the other things we already have in place for this particular problem, I'm just changing the type of the method. And I'll have to evaluate all of this because I have closed down things. Okay. And I have also arrived at 14.78 something. Did everybody get their false position to work? No? I will meanwhile get to count up number of iterations. This is something that I asked you to do. And I'm not gonna print. I'm gonna print things outside of the loop. So in 16 errors, it appears that I arrived at such a value that my absolute error is 0. That's probably because of the roundup errors that are happening in iterations. because otherwise in a nonlinear function I don't really expect to strike that zero precisely. Okay. And this is also one of the points that sometimes a little unexpected things can happen, and possibly I might have an infinite loop going. And to prevent from that, we often actually put a maximum number of iterations as something large, but still I can say, hey, it's 100,000, but stop at 100,000. And the way we actually put that in there is we just say and here, and iteration less than. So it's good to have a mechanism to stop just in case something odd happens and you keep iterating. Infinite loops are not good. Okay. So this is going to give me additional stopping criterion. Kind of always a good idea. And also because there's no guarantee that you're going to find the root, at some point you have to stop. Okay. If you haven't found it in 100,000 iterations, well, most likely, whatever you find is the best you're going to get anyway. So may as well stop the cycles and not keep going. And change something either about the method or the function or so forth. And you might even want to, if your number of iterations is equal to maximum number of iterations for some reason, just say so. Max allowed number of iterations reached. So something didn't really go as expected. Just understand that the process is not perfect, nor guaranteed. Did everybody get false position working? No? Where are you stuck if you're stuck?
Since the root is NaN.
Okay, so this is where you possibly need this. Okay, so something has gone wrong other than this. So I'm going to take, Ningyu, can you take a look? So possibly this was not typed in correctly. So instead of a midpoint, everybody else okay? You're not okay, flag Ningyu down. Okay. So just as a recap, we have some way of estimating my next approximation. I have to continuously recompute the error. I have to decide when is this error small enough and when is it that I'm going to stop. So this is this epsilon, okay? And I could actually modify this to use relative error. That would be a more robust way that would kind of work similarly for different types of functions. And also it's a good idea to kind of stop or have additional stopping criterion in terms of maximum number of iterations, because most likely if you're hitting there, something else is wrong with the problem. And the way you're looking for it, if you didn't find it really within 100,000 iterations, you might not be able to do better anyway. Yeah. Questions? So what we call, and what you already touched upon in your calculus class is the idea of convergence. Okay? So whenever you're looking for something or you have some sort of series or something, question is, are you going to arrive at your destination with by adding more elements to some summation. In this case, question is, as we iterate through these approximations, are we going to get close to the root? Okay? And I can get there sooner or later. And here is an example in some problem. This is a relative error, and it's a true error because it was evaluated at some problem where I actually knew the true solution. So we can see that bisection kind of can go off and up and down, and the false position, if it works well on this interval, will actually go there faster. In this particular case, actually that wasn't the case. I think we did bisection in 14 iterations, and this one is 16. But we also had that absolute error of 0 at the end of false position, at least on my computer, indicating that there's possibly some round-off error issues involved. Okay? So there is no guarantee, but we often plot this relative error on log scale. Okay? And this log scale kind of tells me how fast I'm getting towards the solution. And we, of course, want to get there faster because that means that when I have to repeat the problem multiple times, I'm going to go work really well. Here's one example where this method would work really badly. Okay? If you had a function that is like f of x to the 10 minus 1, and you worked on this, so if you look at this function, it's 1 is its 0. But if I looked at 0 and 1.2 or so, okay, there's a very steep, I'm very far away from its linear approximation, essentially. And my false position method would, at this iteration, say, okay, this is your next XR, then this is the next one, this is the next one, this is the next one. This is basically graphically what it does, right? It linearizes the function and it sets this 0, that linearized version as your next iteration. Then I redo that, right? So you can do this graphically. And you can see that you're like really slowly getting towards this. And bisection in this case would actually go there faster. Okay? So there's kind of not, depending how nonlinear your function is, there's no guarantee that one method will work well for all of the problems. Which is why we need a selection of methods so we can actually tailor them to the problems we have. So as a summary, in these bracketing methods, I have to have this starting interval. And then I basically find a way to look at what is my next subinterval. And in bisection and false position, we choose that subinterval somewhat differently. But basically, I kind of keep zooming into my root. The next option is basically, okay, do I really have to always have this bracket and look for it first? Sometimes we don't want to do that. And we want to start just from one value and keep going. And those are called open methods. They require one guess. They're usually faster if they work. And if they don't work, they just don't work. Okay? So you have to keep guessing. And that's something that we have to. This convergence is not guaranteed because you don't sometimes even know that you have a root nearby. So here's one way to design a method. It's somewhat confusing, but it is a way. So I start with my f of x is equal to 0. And then I rearrange algebraically this equation to formulate it as x equals to something else, g of x, so that these two things are the same equation, they're equivalent. Okay? So let's say that I have x squared plus x minus 1 is equal to 0. I would rearrange that to have x equals to minus x squared plus 1. Everybody sees that one? Now in sine of x is equal to 0, that's not necessarily obvious. I could rearrange that to x is equal to sine of x plus x. Okay? Now, if I wanted to devise a method out of this, it would be kind of conceptually easy. I start with a value, x0, And then my next value is this g of x0. Okay? Because x has to be equal to g of x. Okay? So in that process, I take one value and then I get closer to the, presumably, to the solution by saying, okay, my next x is that g of x. And as I keep going, I hope that this actually gets to some x where x is indeed equal to g of x. So I kind of start with what I wanted to happen, and then I hope that it's going to happen. There's no guarantee. So a lot of numerical methods work like that. You kind of start from a process and you hope it works. And actually this, but conceptually it's really simple. So you again stop when you get close enough in your approximate error. Now, there may be several ways to rearrange equations, and some of them will work, this equation, and some of them will work and some of them will not. And when they don't, they kind of work really badly. Actually, there's a rule that says that this will converge only if this g of x that you found, only if its slope is limited by 1. And here's why. So basically, let's say that you find this x is equal to g of x. You found g. Okay? So that your problem is equivalent to finding x such that x is equal to g of x. Okay, great. Let's say that you have it. Geometrically, what you're looking for an intersection between two functions. One of them is y is equal to x, and the other one is y is equal to g of x, correct? If you can plot those two, look for an intersection, that's the solution to your problem, geometrically. So let's look at it geometrically here, right now. So this is your y, or y1 is equal to x. And this is y2 is equal to g of x. And you're looking for this intersection right here. Okay? So let's say you start from this x0. Okay? Some value, some initial guess. This rule says that your next x1 should be g of x0, correct? So that value is right here, this value. This is its value. Okay? Now, if I walk myself over in a straight line to this function y is equal to x, for this function, its y value is g of x because I walked on a straight line parallel to this line below. But it's on a line where y's and x's are the same, so its x value is actually my x1. Is everybody following this geometrical argument? Yes? Okay, great. So this is my x1. So what is now my x2? x2 is, I just get up here to y2 is equal to g of x. So this is where my x2 is, and I repeat the process. I walk myself over to this function where both x's and y's are equal, and I find my x2. See? So basically, if I have a relatively gentle slope of this function g of x, I'm going to kind of slide, in this process, I'm going to slide down to my actual value that I'm looking for. However, if not, and here's an example where that is not the case, here's my x0, then this is my g of x0. I walk myself over to this y is equal to x, and this value is right here. Okay. Now I go to g of x, and it's right here. I walk myself, so this actually still works. And it's just gentle slope, but negative. I have positive gentle slope and negative gentle slope. Now, if I have a slope of g of x that is not so gentle, what will happen? I start here from x0. I go to this is my g of x0. Okay. I walk over to this function y is equal to x. I'm right here. So this is my x1 right here. Value of that x1 now, it's kind of much larger, right? This is my g of x1. And as I walk over, I kind of get further and further away from the intersection of these two. I kind of spiral outwards. And that's because the slope of g of x is not so gentle. And same for not so gentle but positive and not so gentle but negative. So this process, if it works, great. Actually, it can work really quickly. But my g has to be appropriate. It's g prime of x, that's the slope of g, right? Has to be an absolute value less than 1. Everybody's kind of doing this. I don't know whether that's because you're sleepy or because you actually understood. Let's give it a shot. So let's do this I have two functions. So let's do b. F of x is x to the 4 minus x minus 10. And I'm looking for x such that this f of x is equal to 0. Can you rearrange that algebraically into a form x equals to g of x? And you can do that in multiple ways. And then we're going to look at the g prime and see whether it works or it doesn't. So what are the multiple ways? Can you come up with at least, can this class cumulatively come up with 2 or 3 ways? So I'm solving for x to the 4 minus x minus 10 is equal to 0. I need to convert that to x equals to some other function, g of x. Well, I'm showing the results now. Never mind. And that. While you're coming up with that, I thought of string. What is one possible way? Can somebody throw? Okay, so x equals to x to the 4 plus 10. Yes? No, x to the 4 minus 10. All right. So I'm solving. I have f of x is x to the 4 minus x minus 10 is equal to 0. And I can rearrange that to x equals to x to the 4, or let's do Python way of doing x to the 4. I'm going to use minus 10. Yes? So that's my g of x. So what does fixed point, let's just give it a try. What does fixed point say? What should be my, so I start from some x0. What should my x0 be? Anybody? 1. Excellent. So let's do that. And then my g of x, so my x1 or next one is g of x. I'm going to actually define myself g of x. And that's going to return x to the 4 minus 10. Yes? That's my g of x. So first, I can actually just kind of try a couple of times. This is what the method would do, right? Started from 1, went to -9, then to 6,000 something. That's not looking good. So this is just me typing things in. More effective way to do this is what? For loop or while loop. So I'm going to start it with error being 1. And I'm going to say while my error is larger than, I don't know, 0.001, my x1 is g of x0, then recompute this error as, I need to import numpy time. Absolute of my x1 minus x0. And to keep this going, after I recompute the error, I gotta replace my x0. Is everybody following? Okay. And that's about it. Compute x1 as g of x0, recompute the error between the two, and then replace x0 with x1, and then keep going until your error goes. Yes? So this speeds up my attempts here. I'm gonna now put these attempts away. And then, well, print that thing that you get at the end. I already kind of had a hunch this might not go so well. So I'm gonna put that number of iterations in there. To stop. So that I don't create an infinite loop. Because if any method could go wrong, fixed point is one of them. Let's try. That's thinking. This means it's taking a long time. Maybe 100,000 was too much. It's too generous. Still working on it. Well, I'm gonna interrupt. I'm gonna give it 10,000. Save. Again. Still too long for 10,000. My computer is slow. Still working. Point is, this is not converging. Okay? No.
Did you add 1 to iterator?
What?
Did you add 1 to iterator?
Yes, I did.
Or did you actually interrupt it?
I interrupted it first time. This is still too long. I'm not
You
sure.
have to check whether the star is gone after.
Yes, it is. Let's save again. Let's try again. I'm gonna stop at 100. Save. It's still, I don't know why. Yes, insanely or even infinity, INF, right? That's divergence. Okay, it didn't go well. Why? What did I say about G? What has to be true about G? Slope, G prime of x, has to be less than 1 on some interval where I'm at. G in this case is x to the 4. Slope will be 3x to the 3. Right? If I take that even with number 2, it's going to be really large. It's not less than 1. Okay? These things work better when my G is x to the 1/3 or something like that. So can you think of another way to frame this? Oh, and then I'm showing the way. Well, oh well. I may as well show it then. So I can actually arrange this as x to the 4 equals to x plus 10, and then do x plus 10 to 1 over 4. Okay? Because that's going to give me a gentler, better slope. Because slope of that is 1 over 4, x plus 10 to minus 3 over 4. Okay? Everybody sees that? Let's give that a shot. So basically I just rearrange this as x to the 4 equals to x to the plus 10. And then my x is equal to x plus 10 to the 1/4. Yes? Let's give that a try. The little analysis on the slide says, so I'm just going to copy. My thing is still working. I don't know. There's something else wrong. Maybe I need to restart my kernel altogether. Okay. So I'm going to arrange this as x plus 10 to the 1 over 4. Okay? And that's what I'm going to return here for G. Everybody following what I did here? So I just copied the code and changed my G. And let's see if this converges. Save. Okay. I can also print number of iterations. There's multiple, yes, so that depends on your starting point. Yes, I can. So in 4 iterations, I got really quickly to. So here's how I changed my G. I rearranged this to be, I basically said x to the 4 is equal to x plus 10, and then my x is equal to this to 1/4. And when I change my G accordingly, I just repeat the same iteration. And now I got to this root within this accuracy real quickly. Let's start change the starting point a little. Let's go negative. I still found the same root. This is still relatively small, though it appears I found a. Let's go plus 100. It seems that I'm stubbornly finding only one root. Let's try 2. There is multiple roots to this function. It's x to the 4, so I have 4 roots potentially. If I have one of them real, there's another real root. Okay? But it seems that whatever starting point I'm picking here out of the blue just by throwing darts, I'm always getting this 1.855559. Let's try with 0. I don't know. Still the same one. Minus 1. I'm stubbornly finding only the same root. This function has more roots. Questions? So how you design G doesn't matter. And around there, in this area we're looking for the root, the slope of that g. Again, slope of g could be different over the entire range of possibilities, but around where you're searching for root, it should be gentle enough. Okay. There's one more faster method, and we're going to get to program it next time, but it's called Newton's method. Newton had a hand in a lot of things. It converges much faster to the root if it converges. It's also using f prime of x. And it's essentially saying, at the point where you start, approximate this function. So it's similar to false position in thinking, it's just not bracketed. So it doesn't have this other part of the bracket. So saying, okay, here approximate f as f prime, and see where this slope takes you. And that's your next iteration. And then do the same thing. And if you're close to the root, this will go really quickly. The problem is that you have to have a way to evaluate f prime, which sometimes when you have data, you can't. Right? If you're just using data. But if you can, this is a pretty fast way. All right, we're going to program this next time.